Okay, so now we're on to here. So, that's not very useful because we don't know how to do explore exploit yet, right? We're saying, okay, we have to learn this function, but we can't do it all the time. You're talking in circles. So we talk about an epsilon greedy, and I just assume everyone knows all their Greek symbols, but that's not always true. So if you're going into research, you need to learn Greek, well, just the Greek alphabet, really. But if you like writing math and stuff, which would be useful for your reports, but it's also just useful to try to impress nerdy people like us on the internet, I'll try to remember to put in things like this. So how you get that character is this epsilon. Why epsilon? Epsilon is just chosen for a lot of things to mean small, right? It's usually a very small value. In general in math, when we're using, at least in the math I see, that's not true everywhere, obviously. In kind of stuff we're doing machine learning, epsilon means some really small part, as small as you can make it, but it might be 0.1, it might be 0.01. It'd be weird if it were over 0.5. What's the idea? The idea here is that we're going to be greedy, like we said before, that you're going to choose the action that gets you the most reward given your current model, but you're going to not do it some probability at the time. It could be a small probability, but that we just give a little bit of noise to say, sometimes I will choose not to follow my policy, and that will mean I'll get to explore something. And over time, your model will get better, your estimates will get better, and you won't lose that much money because epsilon's pretty small. This is the simplest way to do that and to take advantage of it, to do explore exploit. You just say epsilon greedy. And we say it's the simplest, but it is actually, the most common too. Like it gets used a lot still, even though, as somebody was pointing out on Piazza, but it's like if you have epsilon, you'll never get to 100%. Like if you want to optimize it and you're randomly sometimes not following your own maybe optimal policy, you're never going to be acting optimally, right? So there's ways to deal with that. You could basically turn off the randomness eventually. So if we write this down as an algorithm, and it's pretty small, but it's good to get used to having the way we're going to write some of this stuff. So this is the way Sutton Bartow write algorithms in their textbook, so it's good to get used to it. It's just pseudocode and kind of mathematically defined, so we just write a couple equations, and that's basically all you need, right? Like you want to implement it in Python, you got to figure out how to define your function and what kind of for loop you're going to use, but it's enough to say initialize some things, maybe set them all to 0, maybe sometimes we'll set them randomly, right? So the initialization could be random. N is not random. This is the number of times A is taken, so this is your count, right? For each bandit. This is a very simple way to keep track of how many times you've pulled each one. And Q is your value function, right? And then the simple algorithm is basically to have some kind of loop, and at every step you're going to do that thing we talked about. So take the maximum action according to your policy, but instead of just taking it and then saying some of the time we're going to explore, we have explicitly some probability, which is 1 minus epsilon, right? So remember I said, well, see, we're not even defining inputs, so there should be inputs to this algorithm would be epsilon, which let's say we default it to be 0.1. What else? K is the number of bandits. I'm going to say 10. And then so the other possibility, you take some random action with a probability epsilon. Now note here, and this will actually come up in some things, it could be random action including A or not. or is it A minus A, right? It could be the set of all actions not including A, right? It's usually this, so you could actually choose A anyways, just randomly, and so then you have to work that out. Depending on which formulation it is, your probability of choosing this is going to be different, right? Because if it includes A, then you have a probability 1 minus epsilon plus another epsilon of picking A. That's something to be aware of. We'll have examples. And then we compute the important parts, right? So the bandit, this is the world in that diagram of agent and world. That's the world. Right, so that's bandit. And which one's agent? That's the next question for somebody to answer. So that just gives us the reward, right? So this is basically how much money you're getting. And then we increase our count, very simple, right? So we now took action A, so we're adding in that table, we're adding something, right? These are functions with just 10 values, so they're literally arrays, right, of just 10 values. And you're just filling them in. And all of RL can be kind of understood that way, as having these tables. The table's going to get two-dimensional at some point, and then eventually we'll replace all the tables with neural networks, but mathematically, they're just tables. So we'll be talking about tables for a little while to understand the math. So you increase that count. So if A was number 2, then I guess we're going to be 0 indexed, I assume. Then we'd have a 1 here, right? And everywhere else would be 0. And then the last thing we do is you update Q, and here's the meat of it, the magic formula. We use a magic formula to update Q. We'll talk about the magic formula next. It's not magic, but it's a very important formula. It's the most important formula in the course, although it's really a class of formulas. This is a Bellman equation. There's many Bellman equations. And so I guess did anybody answer? What's the agent? The world is that part bandit A. Nobody answered. I'll change the color to give people time. What part of this is the agent? What part of it is the policy? Okay, because in my view, in my value of it, right, I had we've got an action that we take, and then we've got a policy that we follow, and that's what gives it to us. Right, so the policy is this thing, right? Tells us what to do given that. In my one, the agent has a model. You could say, you know, that's the model is what the agent thinks about, is trying to decide what to do. And the model is this, right? Because you've got some statistics that you use to basically make these estimates. And the action, obviously, is the action. What else am I missing? That's the world. And yeah, my interpretation of it is that the agent is really just the model.